to the cloud. All right, I think I'm set up. I think I have everything. Let's talk about the test. I've graded them and I put the grades in Canvas. I don't have them for you because I still have a few students who need to take the test. So that's the way I do it. I don't hand out the test until everyone's taken it. I need to talk with those students to finalize a date. There's been some conflicts with scheduling of that. So I will hopefully work that out and get them to you next week sometime. All right. So until then, stay tuned. Here are the things that I noticed on the test. Probably the biggest thing I noticed was cleanliness and neatness of work. That was probably the biggest thing. Like, there are students who are neat, there are students who aren't. And neatness doesn't mean that you don't know. Like, if you're neat, you could get it all wrong. And if it's sloppy, you could get it all right. But anyone who's transitioning here from college algebra up through pre-cal, calculus, right? If you're going to do that, you have to think about at some point down the road in your career path that you choose, you will need to be able to communicate your ideas to your colleagues, okay? You will have to be able to put your ideas down on paper and be able to present that to somebody. And if they can't look at it and it looks like chicken scratch crap, you need to work on that, okay? That's the way I was in the beginning. My work looked terrible. And I sat there and said, well, it's right, it's right. But I understand now. It's more about, it's like writing a paper. If you don't have periods, if you write a paper the way you text somebody, those are two different standards. And so when you're turning in the test, that should be you not only showing your professor what you know, but also showing them you know how to communicate that in a clear way. So it's something to work on. Okay, it's something to work on for a lot of people. All right, I don't take off for it. Okay, as long as I can make sense out of it. But that was probably the biggest thing I noticed, is like, this needs to be cleaned up. So, and then when I hand them back, we can talk about what you got wrong and things like that. And I'll give you the solutions. Any questions though? Any questions? Let's see, we're recording. We ready to roll here? I forgot my glasses, so I can still see, but they're my sunglasses. Yeah, those won't work. My wife makes fun of me because I buy the $9 sunglasses from Home Depot because I lose them and I break them. So I refuse to wear like $200 sunglasses. All right, here we go. Everybody at home ready?
Yes.
Yes. Okay. All right. So we were covering last time composition of functions, right? Composition with domains. And so 6.1 is in the past. We're going to move to 6.2. We're building up to talking about exponential and logarithmic functions. That's what we're building up to. Before we can get to those two functions, which will be the last functions we talk about in this class, we have to make sure we're clear on this concept of one-to-one functions and inverse functions. So one-to-one functions, there's a lot of definitions here. I'm going to provide this entire document. Everything that's here, I will send that to you later as an email. Okay, so everything here, don't feel like you have to write this all down. This is all in the ebook. Just pay attention, ask questions if you have any. So the first thing we have here is a definition of what it is to be a one-to-one function. And so the definition says a function, okay, a function is said to be one-to-one if any two different inputs in the domain correspond to two different outputs in the range. So we have pictures here. These are those pictures that we've kind of been using all semester. The left side is a domain, the right side is the range, and a function is taking these things over, starting here and sending them somewhere. So notice in the first picture that for every input that's different, you have a different output. Okay, none of these go to the same place. And that's what makes a function one-to-one. This second example is an example, well, first of all, is it a function? So what does it mean to be a function? A function means you plug something in and you get exactly one thing out. Okay, one input, one output. So this one input, does it go to one place? Yes. Does this one input go to one place? Yes. Does this one input go to one place? Yes. So it is a function, but it's not an it's not one-to-one because these two inputs that are different go to the same output. We can't have that happen to be one-to-one. All right. So this is a function that's not one-to-one. How about this one? It's not a function because this input goes to two outputs, and that's impossible. This is like when I was talking about functions and saying functions are like car washes. You put a car in, comes out the other side clean. This is like putting a car in and getting two cars out the other side. That would be a moneymaker, right? But it's not possible, right? So this violates being a function. So is it one-to-one? Does each input, different inputs go to different outputs? Well, these two inputs are different, right? And the outputs are different also, right? Like this one doesn't go to one of those and this doesn't go here, right? So it almost looks like it would qualify for being one-to-one, but it's not. Why? What does it say here? A what is one-to-one? A function is one-to-one. You first have to have it be a function. If it fails to be a function, you can't talk about being one-to-one. So this right here, just by the fact that it's not a function, you can't even talk about one-to-one. Any questions? There's two different ideas here, what it means to be a function and what it means to be a one-to-one function. They're two different ideas. I think the one-to-one makes sense. Like one input, one output, and it's that way both directions, right? If you go left to right or right to left, everything is one line back and forth. All right. Next thing. The horizontal line test. So you all remember the vertical line test, right? The vertical line test is the test that we use to check to see if something is a function. We draw vertical lines. We say, hey, as long as we don't hit more than once, right, we've got a function. That's the check for a function. Well, we have a very easy way to check to see if a function has an inverse, and that is the horizontal line test. So it says here, if every horizontal line intersects the graph of a function f in at most one point, then it is one-to-one. So they give you two examples here. The one on the left, is this a function? The blue curve is a function. It passes the vertical line test. Vertical lines never hit more than once. But it is not one-to-one because if I draw a horizontal line, it can hit twice. In fact, it can hit twice, anywhere here. Down here, it doesn't hit anything, right? That's okay. Just because down here doesn't hit anything, who cares, right? The graph's not even down there. All we need for it to fail the horizontal line test is for at one of these lines, I hit more than once. So this one here would be a function, yes. 1-to-1, 1-1, no, right? All right, how about this blue one? Is it a function? Yes, passes the vertical line test. Yes, it's a function. Is it one-to-one? Yes, if I draw horizontal lines, I never hit more than once. All right, pretty straightforward. Let me give you another one. A sideways parabola. Is it one-to-one? Is it one-to-one? All right, so let me ask it a different way. Does it pass the horizontal line test? Well, yes, it does, but the horizontal line test can only be run if you're looking at a what? A function, right? So the first thing we have to notice here is that this fails the vertical line test, right? So it's not a function. As soon as it's not a function, the one-to-one, you can't even talk about it, okay? You can't talk about one-to-one if you don't have a function. So here we would say function no, done, right? How about a circle? It's not a function, right? And it would fail the vertical, both tests, wouldn't it? It would fail on both. All right. Any questions? All right, so with this idea, we now define something. I'm sure you've heard of this before. It's called the inverse function. So it says, suppose that you have a function, y equals f of x. So they're telling you it's a one-to-one function. Let's say we start with that, right? Start with a function that's one-to-one. The correspondence from the range of f to the domain of f is called the inverse function of f. And the symbol we use is f with this little -1 to denote the inverse. Okay, so what do they mean? All they're saying is, if the function is one-to-one, right? So if every input here goes to exactly one place here, right? Then there should be some way to send all these back to where they came from. And where they go back to can only be one place, right? There can't be two different places. I talked about this in class 2 classes ago. I think I told you, you remember I said I have this function that's spitting out 4, right? And so you plug in a number, it spits out 4, plug in a number, it spits out 9, plug in a number, it spits out 16. I tried to convince you that this number was squaring things, right? And so then I said, okay, here's 4. Where did it come from? And everyone said 2, right? I said, nope, it came from -2. So that was an example where you can't tell where it came from. That's kind of what this is saying. As long as we know that every input here goes to exactly one place, then we should be able to find a way to send it back. If it's one-to-one, this should work. If it wasn't one-to-one, let me show you the picture over here. Let's say this wasn't one-to-one, and we had this happen. An input went to 2 outputs, right? Oh, sorry, can't have that. I meant to do this. Input went here, and let's say this one went here, and then this one went here, like that. So for this is a function, but it's not one-to-one, right? Because these two go to the same place. So if I asked you to send this back to where it came from, you'd have to send it back to 2 different things. And functions can't do that. Functions can't send something back or go to 2 different places. That's the 2 cars coming out of the car wash. So as long as we have this straight one-to-one relationship, then there should be some function that sends everything back, and that's called the inverse function, right? And we denote it with a little -1 above the f. So I want to show you something. I'm going to show you that same picture, but I want us to think about it slightly different. If we have f going here, and let's say it's one-to-one, okay, f, and it's a one-to-one function, then if I have an inverse that takes it back. So if I take, let's say A, right, and I plug A in here, and let's say it spits out B, then the inverse function will take B and send it back to A, right? So F takes A in and spits out B. The inverse takes in B and spits out A. That's basically what this picture is saying. If I start with A in the F function, send it through, it'll spit out B. If I take that answer and plug it into the inverse, it'll send it back to A, right?
Is that what inverse means, where you can flip it?
Where you can take it back, send it back. Yep. All right, so we're going to be able to clarify what inverse is, I think, as we move on. But here is one of the very, very nice properties of inverse functions. The graph of a one-to-one function f and the graph of its inverse function, f inverse, are symmetric with respect to the line x equals y. Okay, what in the world are they talking about? All right, so first of all, notice that this right here, y equals x, that's the perfect diagonal line. That's y equals 1x plus 0. Think of the good old-fashioned formula for the equation of a line, y equals mx plus b. Y equals x is really just a 1 in front of the x and then no number next to it, right? So the y-intercept is 0 and the slope is 1, right? And that's what this diagonal line is. Right? Goes through 0, up 1 over 1, up 1 over 1. That function actually has a very special name. It's called the identity. The identity function. All right. What this theorem says is that if you have a function that's 1-to-1, like look at the blue one. Is the blue one 1-to-1? Yeah, it passes the vertical and horizontal line test, right? If we were to graph the inverse of it, here's what the inverse, they're telling you this is what the inverse would look like. And notice that they are a reflection or they are symmetric over this diagonal. So it's almost like you'd have to go up, turn your head sideways a little bit, right? I'm sure you can all see it, right? Just turn your head and it's like a mirror image over that diagonal line. All functions and their inverses together will have that property. All right? All of them. Why? I don't know. Let's do an example. So here's our first example of the day. You're given this function f, and you're asked to graph the inverse of it. Okay, graph the inverse. Now, first of all, is that a 1-to-1 function? Passes vertical and horizontal line test, right? So we're good. So here's the way I'd like for you to think about this. Let's just look at this first point right here, right? That's the point 2, 1. That means that f, right? 2 went in, got sent through f, and came out as 1, right? So where's the inverse function going to take the 1? Back to 2, right? So the inverse function should take 1 back to 2, right? Which I can look at as the point 1, 2. This point lives on the inverse function. See, I'm trying to graph the inverse. So what I do is I say, all right, if this point lives on f, then this point lives on its inverse. And I can do that for every point that I have, which is basically just flip them over, right? Flip the coordinates. So I know 1, 2 lives on there. What about this? This tells me what point lives on the inverse. 0, -1. And then this tells me that the point -1, -2 lives on there, right? So I'm going to plot these points now. 1, 2. So that means I go to the right 1, up 2. That point lives there. 0, -1. That just means down 1 like this. And -1, -2 is to the left 1, down 2. That's here. You got it? Those are those 3 points. I'm also going to draw the diagonal, the identity. I want to draw it in here. And now it's not part of my answer, but it's going to help me draw things. The diagonal is the line that goes through 0, 0, the origin, and goes up 1 over 1, up 1 over 1, up 1 over 1. So it's going to look, I'm going to do it kind of dashed. Like this. There's my diagonal. And so if I connect this point to this point with red and then this point to this point, I should have the inverse function here. There you go. That's f inverse. It is a perfect symmetric reflection over the identity, right? By the way, is the inverse function 1-to-1? It should be. It needs to be, right? So if you start with the 1-to-1 function f, its inverse must also be 1-to-1 because they have to go back and forth. And so you have to have that very strong condition of 1-to-1 on both of them. Questions on that? Yes, go ahead. The identity function is 1-to-1. You tell me. The question is the identity a 1-to-1 function? My answer is yes. Then the next question was, what is the inverse of the identity function? It's itself. It is its own inverse. So think about this. let's act like y'all are the identity function. Okay, so I'm going to give you a number. Ready? 3. What do you spit out? Okay, now we need to send it back to 3. So it's the same function, right? It doesn't do anything to the input. Goes to 3, comes back. Goes to 4, comes back 4. So it is a reflection of itself over the identity because it's itself, right? Good question. The identity function always goes through the origin because the identity function is exactly the function y equals x. And so remember this whole idea of y equals mx plus b. If it's just x, the slope has to be 1 and b has to be 0. B is the y-intercept, so it will always go through the origin. Okay, so like what if you had something that looked like, here's my diagonal. You're saying something that was always over here? Like that, maybe? Okay, is it 1-to-1? Okay, so its inverse would look like this. Not very good. Not very good, but it's supposed to be a reflection of itself. Yeah. So that would also, that blue one is also a 1-to-1 function. Any other questions? So not every function has an inverse because not every function is 1-to-1, right? So is every 1-to-1 function invertible? Does every 1-to-1 function have an inverse? Can we find it? Like if I just give you a function and ask you, is it 1-to-1? Can you find it? These are open questions. I'm going to answer them as we go today. Trying to get you to think ahead here. All right, so where are we here? We had that, we had this. Okay, so we did this. All right, now, at this point, if I show you a picture, a graph of something, you should be able to tell me, 1, whether or not it's a function or not, 2, whether or not it has an inverse, right? Meaning whether or not it's 1-to-1. And then if I give you the graph, you should be able to draw me the inverse because all you have to do is draw the diagonal and then do a reflection, maybe pick some points, flip the X and Y coordinates, and you should be good, right? That's where we are. Now let's act like we don't have any pictures, all right? Let's say we don't have any pictures. I hand you 2 functions and I ask you, are these inverses of one another? Do these undo each other, right? How can you figure that out? That's the next note. How do we verify that we have an inverse if we're given 2 functions? So to show that f and f inverse are indeed inverses, we must show both of these are true. There are 2 things we have to show in order to verify that 2 functions are inverses. F of f inverse of x, when you compose these together, should spit out x. And when you do it the other way, f inverse of f of x, it should spit out x. So I'm going to show you both of these in pictures, what we're trying to show. This first picture says that for these to be inverses, it says if we first feed x, right, x here, if we first feed it into the inverse, so if we put x here and send it through the inverse function, that's that inside part, right? It'll come out over here on this side as f inverse, not prime, sorry, f inverse of x. That's where this would go, right? That would be sent over here like that. X would go to f inverse. Now, where do we need that to go back to? Where do we need f to take that? Back to x, right? That's what this is saying. If I take x, I feed it through the f inverse, and then I take that answer and feed it back through f, it should come out unchanged. That's like me saying, hey, the 3, you spit back 3, that whole idea. It's like a little circle you have to complete. This is the same exact expression, except the x is starting on the left side. So this is saying if we start it with the x here, it has to go through the f first, come through as f of x, then the inverse function has to send it back to x. That's what it takes to verify that two functions are inverses of one another. Two things. We should do an example. So I'm going to do this first one. I'm going to do it a little bit different than the book did it here. What I'm going to do, I'm going to phrase it a little bit different, because right now they're saying, please verify that this is true. Okay, they're saying verify this is true. I want to change the problem. I want to say, let's call the first one g of x is equal to x cubed. And let's call the other function f of x and make it the cube root of x. All right, and let's act like this wasn't given to us. And now let me ask you this question. Are these inverses? Well, if they are, then when you compose them together, they should kill each other off, right? So that means the first thing I would need to do is I would need to show that when you take f and plug into it g of x, what should pop out? Just x. That's the first thing I have to show. The second thing I'm going to need to show is that when you do it the other way, you take g and plug the f function into it, it should also spit out x. This is what I have to show. So let's start with the first one. This is where it goes back to 2 classes ago when we were doing composition. This means f, and inside of it goes what? G of x, which is x cubed, right? All right. Remember, everyone, this is a question, right? Is this true, right? Is this equal to this? Is it equal to x? Well, we're working down the left-hand side. Let's see what it becomes. So f, replace g of x with this. Now take x cubed and plug it in right here into the f function. So if we do that, we're going to take the x cubed and take the cube root of it, right? And what happens when you take the cube root of x cubed? They cancel each other out and you just get x. Check, right? You compose them this way and you got x out. That by itself is not enough. That alone isn't enough. You have to show it the other way too. So here on this one, I need to do g, and inside of g, I'm putting f. F is the cube root of x. And then what does g do to the cube root of x? What does g do to anything you give it? It cubes it, right? So I'm going to take the cube root of x and cube it, which has the same effect as over here, right? This will just be x. Check. Okay, are these inverses? Yes. All right. The first 2 examples are easy examples. All right. Let's do this one. So I want you to do the same way. Let's call this one g of x. And I want you to show or answer the question, are these inverses? All right, so let's look at the 2 things we have to do. The first thing, I need to take f, plug g in, and see if it's x, right? Then I have to take g, plug f in, and see if that gives me x or not. So on the left one, I take f, inside of it goes g. G is the 1/2 x minus 3. Be real careful here. This is where students start making mistakes. All I did was replace g in here. There's g. That G is now getting plugged into F. Where is it going to go? In for X, right? Right here. So it replaces that. So this whole thing needs to get hit by a 2. Multiplied by 2, and then add 3. So the way I'm going to write that is like this. 2 times whatever I'm plugging in plus 3. And I'm plugging in the green. So 1/2 X minus 3. And do you see that the 2 and the half will kill each other off? Right, these go away, which leaves you just the X minus 3 plus 3. And now the 3's kill each other off, and you just get X. So far, so good, right? Halfway there, we've shown that when you do that composition, you get X. The next way, G, now into G goes F. And now when we take this, we're going to be plugging it into the X on the G function instead. So I should have 1/2 parenthesis, then everything I'm plugging in minus 3. So I'm about to plug all of this stuff in for that X. I put parentheses around it just so you could see that this is the thing I'm plugging in. And now the parentheses I don't necessarily need, right? These parentheses can go away. And once I get rid of those parentheses, the 3's will cancel. And you get 1/2 of 2X, and 1/2 of 2X is just X, so it checks. Are there any questions on the algebra, the composition? Amanda? What part?
I know it's part of the basic, but why did the 2 cancel out on the 2 on the bottom of the half and not the half?
Right here?
Yeah.
Because order of operations, I have to do everything in this parentheses first. So I have to figure out what this is, right? Yes, I have 2 terms. Do you see I have 2 terms here? So I have to, if I'm going to do this 1/2 through, right? If I'm going to do it, I would have to do the 1/2 to here and here. Over here, because this is multiplication, let me write it this way. 2, you have a good question, all right? This is just, it's these little nuances. We don't need this parenthesis because this is multiplication here and that's multiplication here. So really this is 2 times 1/2 times X minus 3. And that's why these can go. Over here, you cannot drop this parenthesis unless you distribute the 1/2 through because we have subtraction here. See the difference? Okay. Any other questions? The 1/2? It wouldn't matter. I mean, you would, if you put the 1/2 through here, you would do it in front of this one and then to here. Is that what you're saying? And then that 1/2 would have to go here and here. And if you did that, then you would have a 3/2 here and a minus 3/2 there, and they would cancel. Yeah. So yeah, as long as you do the algebra correctly, it should work both ways. I feel like I should let you try this one. Or maybe I'm getting too far ahead of myself if I do that. What do you think? Do y'all want to try that on your own? You want me to give you a few minutes to see if you can get anywhere with it? I want you to do the same thing we did before. I'm giving you F and G, and I want you to answer the question, are these inverses? Do you want to try it or do you want me to work through it? It's up to you. What do you want? You want to try it? Okay, go for it. You're trying, I'll write what you're trying to do. Write the 2 things, right? Trying to do F of G of X. And you want to show that that's X. And then the next thing that you want to show is that G of F of X equals X. This is what we want to show, right? We want to show that both of those are true. So in math, it's very common for us to write this when we're trying to show something. We write WTS. WTS, want to show. I'm not making that up. That is truly, mathematicians use that notation because we don't like writing words. So WTS, we want to show that that's true, and we want to show that that's true. All right. So see if you can. See if you can do it. The algebra in here might get a little bit messy, or it may not. Depends on how you do it. If you have a question, let me know. I can come by and take a look. I'm going to slowly start working this. Yeah, why did I do that? I did it right over there, though. Yeah, thank you. X minus 1. So if the composition causes you any issues, this is going to be hard to do, right? You have to understand how to do the composition. Are there any questions on what I've written up here? Did you all get the same sort of thing here? How about this first one? I put this in parentheses because I wanted everyone to see like the G function, the F function takes 1, divides by what you put into it and subtracts 1. So it takes 1, divides by what you put into it and subtracts 1. So I put it in parentheses. I don't need the parentheses because there's no number in front of it. I'm not squaring it. I'm not multiplying through by 2. So I can just drop the parentheses here, can't I? So what would I get on the bottom then if I drop the parentheses? Just 1 over x, right? Because the plus 1 minus 1 will cancel. And so we just get 1 over x, or sorry, 1 over x. And anytime you have 1 over a fraction, you can reciprocate the fraction on the bottom. So you just turn the 1 over x into x over 1, which is just x. So it checks that way. On this one, same thing. Plug 1 over x minus 1 into g. So we replace the x in the g function with 1 over x minus 1. This is 1 over a fraction, right? So again, it reciprocates. So that just becomes x minus 1. And then we have the plus 1 already out here. And that cancels out. You just get x. There it is. Questions? There was an additional question on this one that I want us to talk about. For what values of x is f of f inverse equal to x? Well, for us, remember, this is the g, right? We replace that with g. So it's asking, for what values of x is f of g of x equal to x? Well, we said f of g of x is equal to x, right? We did all this algebra, everything worked out. But is there anything that would cause a problem here? This goes back to 2 classes ago. Domains of compositions. So yeah, think about g, right? G, who gets x here first? F or g? G. Is there anything you can't plug into g? Can't plug 0 into this, right? Right. 0 is the only thing you can't plug in to this. Right. So what I need to do is I need to do this down on a separate thing here. We're looking at f of g of x. And basically what we're asking for is a domain of this. And I told you when we do domains, you have to look at both the functions. So let me copy these down. F of x was, this is a good reminder of something we looked at in the past. G of x is 1 over x plus 1. So when you're asking for the domain of the composition, there were 2 things you had to look at. Do you all remember this? This is a while back. First thing was, what's the domain of g? So we have to take the domain of the inner function, right? So the domain of the inner function is anything but 0, right? Can't plug 0 into it. So here I'm just going to put everything but 0. So I'm just going to put x can't be 0. But when we take this and plug it into this, what can't happen? We need to make sure this cannot be what? Positive 1. Because if this goes in to here and becomes a positive 1, we get 0 down here, don't we? And that'll mess up the f function. So if you look back in your notes, I said we got to figure out what outputs of g will cause problems for f. So from that, I need this 1 over x plus 1, right? We want to make sure that that's not equal to 1, yes? Because if this output goes right here and is a 1, we're in trouble. So I have to figure out when this happens. If it happens, does it happen? Well, why don't we subtract 1 on both sides? Then we're saying 1 over x cannot be what? 0? So is 1 over x 0 ever? No, why not? Do I? The denominator can't be 0, but the numerator can't change. So this can never be 0. There's a couple of ways to look at this. The first way I want you to think about it, just for now, for this particular example, is that we should actually know what that looks like if we graphed it. This is one of our rational functions that looks like this. That's the graph of 1 over x. And that is never 0. It never hits the x-axis, right? But I don't want you to look at it that way. I want you to look at it a different way. And this is the way you need to look at it from a calculus perspective. In general, and this goes for any time in your life doing math, if you ever have a fraction equal to 0, if you're wanting to know when that's true, let's call the fraction a on top and b on the bottom, all right? If you ever want to know when this is true, all you have to do is ask yourself one question. When is the top 0? A fraction can only be 0 if the numerator is 0. That's what I'm saying. A fraction can only be 0 if the numerator is 0. It's impossible to make a fraction equal to 0 by messing with the denominator. It's only the numerator that can make it 0. Now, if you don't believe me, all you'd ever have to do is multiply both sides by b, cancel the b's, you'll get a equals 0 times b, which is 0. So you wind up with the same equation, a equals 0. So when we're looking at that problem there, and I say to myself, okay, when is 1 over x, equal to 0? Well, that's not going to happen, right? It's never going to be equal to 0 because the top one can't be 0. So do we have any domain issues here from the second part? No, because this can never happen, right? So the only time, so to answer the question, for what values of x is that composition chain rule that, this composition spit out x? It will spit out x so as long as you're not plugging in what? 0. You try and plug in 0, G will mess up. So you plug in anything other than 0, like let's say I plugged in 2, what should come out? 2, because it can go through the chain, come back as 2. If I plug in 5, it's going to come back as 5. Is there a question? It's okay. It's okay. I'm glad you're thinking. So you were thinking like, what if this was negative 0.5, then that would become negative 1, then this would become 0, but 0 doesn't mess that up. Yeah. Yeah. I'm glad you're at least thinking through trying to figure out if there's something else, right? Okay. That was it. Those are kind of lame. All right, it's all right. We'll do some others. All right, so now we move on. So this is a note. If we're actually given a function, this is the final kind of nice thing for today. If somebody gives us a function, if it's 1-to-1, we should be able to find its inverse by doing the following method. So we know if we're given two functions, we can check to see if they're inverses, but what if we're just given one and asked, hey, go find its inverse? Here's the method we do. We replace f of x with y. We switch the x's and y's. We solve for y, and we replace that with f inverse of x. I'm going to just copy these down, and we're going to do an example. So we're going to start with a very simple example here. Here's a function, 2x plus 3. I want us to find the inverse and then graph both of them together. So here we go. Here's how I find the inverse. I start with the original function. Step one is I replace f of x with y. So I turn this into a y. That's step one. Step two, what I do for step two is everywhere I see an x, I turn it into a y. Everywhere I see a y, I turn it into an x. The reason we're doing that is because when you have an inverse function, that's exactly what happens. The x's and y's switch places. So we're going to do that right now. I'm going to make this side x, and this becomes 2y plus 3. And now I do my third step. I want to solve for y. So can you solve for y here? How do we do that? Subtract 3 on both sides. And divide by 2. So when I divide by 2, I would have this x over 2 minus 3 over 2 equals y. That's one way I could write it. I could have written it x minus 3, the whole thing divided by 2. It's another way I could have written it. Or I could have done 1/2 x minus 3/2. That's another way I could have written it. All three of these are equivalent. When you divide the left side by 2, it can be any of these, right? They're all the same. That should be the inverse. So step 4 is I replace the y with f inverse. There we go. There's the function. the inverse function. I'm supposed to graph these now. Are these easy to graph? First one, that's a line, right? Y-intercept of 3, slope of 2. So I go to the y-axis, I go up 3, 1, 2, 3. There's a point, and then I have a slope of 2, so up 2, to the right 1. This is the rough sketch of f of x equals 2x plus 3. That didn't work. Yeah. Right? Now let me try the inverse. So the inverse is also a line, right? The y-intercept of this is -3/2. So I go down. -3/2 is about what? Not about, it is exactly -1.5. So I go down 1.5. And now to get to another point, I need to go, here's the slope, up 1 to the right 2, up 1, right 2. So if I go up 1, I should be here, and to the right 2, 1, 2. All right, it's about like this. Now I'm going to draw the identity in here. They look kind of like reflections, don't they? It'd probably be better if I went to like a graphing software and did it just to confirm it. The first one was 2x plus 3, and the other one was 0.5x minus 1.5. And then I may as well graph the identity. I think that's pretty convincing, yes? All right. See if you can do this one. This one's a little tricky. I want you to find the inverse. So you're going to follow you're going to follow those steps. The algebra in this one is a little bit weird. So I'm curious to see how you do with it. I'll give you a few minutes. These are the types of problems I like to put on tests because it tests your algebra. So everyone should have that, right? Just replace f of x with y. Now switch all your x's and y's. Everywhere you see x, put y. Everywhere you see y, put x. So the trouble here is that you have to get y by itself now, right? In the previous problem, it was easy. It was a linear equation. You just move stuff around, divided by 2, you were good. Here, getting y by itself is not as obvious. So does anyone have any ideas on how we could do that? Let's clear the fractions out. Good. Let's multiply both sides by y minus 1. We do it on the left and we do it on the right. That will clear out the fraction on the right-hand side. All agree? Now on the left-hand side, make sure you put that y minus 1 in parentheses because it's going to multiply times the x. Let's go ahead and write down the line that we have now. Y minus 1 times x equals 2y plus 1. Okay? We're trying to get y by itself. Can I just subtract 1 now? If I subtract 1, right? If I subtract 1 and then divide by 2, I will have a y by itself, won't I? But what's wrong with that? You still have a y on the other side, right? It's important that the idea here is not to get a y by itself. It's to get all y's by themselves on one side of the equation. So I'm not going to subtract here the 1 yet. What I'm going to do first is distribute the x through. On this side, I'm going to distribute, get xy minus x equals 2y plus 1. Now at this point, I'm going to highlight the 2 terms in the equation that have y's in them. Those 2, right? I'm going to move those both to one side of the equation. And everything that does not have a y is going to go to the other side of the equation. So the way I'm going to choose to do that is I'm going to move this to the left. And then I'm going to take the thing that doesn't have a y, this negative x, and then I'm going to move it to the right. Now, when I say move it to the left and to the right, what I mean is I'm going to subtract 2y here, and I'm going to add x, right, to both sides. So what does my new line look like? What's the new equation? 2y, is it 2y or negative 2y, right? So you said negative 2y plus xy equals x plus 1. So by moving this one to the left, it became negative. And then moving the negative x to the right, it became positive. By the way, you could have written this the other way around. You could have put xy minus 2y. It's up to you. Okay, so why do you think I did that? Why do you think I moved all the y's to one side, all the stuff that's not y's to the other? You can factor out a y, right? Greatest common factor on the left-hand side. They both, well, not greatest common factor. You want to just factor the y out. So I'm going to pull a y out of both. And I get negative 2 plus x equals x plus 1. And we're almost there. How can I get this y by itself now? Divide by this entire factor. So I will now divide both sides by negative 2 plus x, divide by negative 2 plus x, and that will give me y. This cancels. We get y equals x plus 1 over, I'm not going to say negative 2 plus x, I'm going to write x minus 2. Is that all right? I just switched the order of the 2. This should be the inverse function. It should be. Now, I believe that this question asks us to verify it. Find the inverse and check the result. How would you check to see if this is truly the inverse of that original function? You would do the f of g of x thing that we did earlier and see if it pops out x, and you'd have to do it both ways. I'm not going to do that for right now. I'm going to let you do that. Questions? That's a little more algebra than the previous problem, right? All right, let's see. Finding the inverse of a domain restricted function. So find the inverse of y equals f of x equals x squared if x is greater than or equal to 0. Okay, so first of all, x squared by itself, that function by itself is not one-to-one because it's a parabola, right? It opens up. But they're telling us, let's restrict the domain. Let's just look when x's are bigger than or equal to 0. So if we take that graph of x squared, here's the whole graph. But we restrict ourselves to only x values inputs that are bigger than or equal to 0, then our graph will only go from here to the right. So that means I can get rid of this part. And this is what we're looking at, just the right side of the parabola. Does this, well, is this a function and does it have an inverse? Yes, it's one-to-one now, right? So by restricting the domain, what we're doing is creating something that does have an inverse. So how do we find it? Well, we go and we do the exact same thing we just did. We take that, we replace f of x with y. Right? We remember x can only be a positive number here. Now what we do is we switch x and y, right? Everywhere we see x, we put y. Everywhere we see y, we put x. And that means y has to be greater than 0 now because we switched everything. And now you solve for y. So how can I get y by itself? Square root, right? So I come in here and I square root. Now, when you come in and square root something, right? When you do it, you have to do plus or minus. So I have to do plus or minus here. So I get plus or minus square root of x equals y, right? It can't be both because then it wouldn't be a function because you have two outputs, right? A positive and negative. So which one is it and why? It's the positive because y is equal to this, right? If you use the minus, then this thing would be negative, which would make y negative, but we just said that y had to be positive, right? Or greater than or equal to 0. So because of this fact right here, because of that, what I can do is throw away the negative answer and just take square root of x is y. Just the positive. Now, what does the graph of that look like? Sorry, we should put f inverse of x here. Isn't square root of x one of those functions you need to know what it looks like? I told you, like when we were first studying those common functions. It looks like this. Starts here at 0 and it goes like this. That's what the square root function looks like. And do those look like reflections of one another over the identity? Yeah. So most of y'all are going to need to take pre-cal, right? Most of y'all need pre-cal. So there's a function in pre-cal that we do this exact thing to. We do a domain restriction. And it always confuses students. And I don't know why, but it does. So here's the function. Don't worry about it. You don't need to write this down or worry about it. There's a function that we study in pre-cal called the sine function, sine of x. And the sine function looks like this. It just goes in both directions, just continues this wave pattern, right? Now, is that a one-to-one function? No, it's not one-to-one, right? That is not one-to-one. It fails the horizontal line test miserably, right? If I draw one horizontal line through there, it's going to hit infinitely many times. So there's no way we could have an inverse unless we restrict the domain. And so what we wind up doing in pre-cal is we restrict it here to here. All right, and we get rid of everything else. Now, in that little region, that's one-to-one. So that piece would have an inverse. And that's called the arc sine function or the inverse sine function. And for some reason, students just have a real hard time with that. It's just this idea that we just did. It's taking this thing that doesn't work if you don't cut off part of it. But if we cut off part, then we can do it. I want to see if you understand that. I want us to do the same thing. I want us to find the inverse of f of x equals x squared. But this time if x is less than or equal to 0. So when I draw the picture of this, I'm only drawing which part of it? Left side. So it's only the left side of the parabola. That's the part we're trying to find the inverse of. Right? So to find its inverse, I first replace the f of x with y. So y equals x squared. And x is less than or equal to 0. Now, everywhere I see an x, I put y. Everywhere I see a y, I put x, including the domain restriction. I do plus or minus or square root on both sides, plus or minus. So plus or minus root x equals y. And now which one of them is it? It's the negative answer. Because the y value has to be negative or 0. If you use the plus, then your y is going to be positive. We need the y to be negative. So we're going to use the negative square root of x here. That should be our inverse function. Okay. What does the graph of that look like? It's the square root function we just drew, but reflected over the x-axis. So it's this graph we drew a minute ago, right? It's that graph, but we're going to reflect it over the x-axis. So it's going to look like this. Do you all see that those are still reflections of one another over the identity? They're still reflections. But that's a very different answer, right? I mean, this answer right here for the inverse function is definitely different than this one. It's because the domain restriction. Just be aware of that. Domain restrictions are important, especially in pre-cal. In pre-cal, we have 6 trigonometric functions that we learn, and all 6 of them have domain restrictions. And all 6 domain restrictions are different for each of the functions. Well, no, sorry, 3 of them are the same, 3 of them are, yeah, there's like groups of 3. So it becomes a little complicated because you got to remember what the domain restrictions are. That's what always catches my Cal 1 and 2 class. They can't remember the domain restrictions on the inverse trig functions. All right, this. I just want to make sure. Nope, it can be other numbers. Like that one I was showing you with the sign, this one right here. For this one, so this restriction that we do here, you can see it's not 0, right? It actually goes between these 2 numbers, and just for your FYI, it just happens to be pi over 2 and negative pi over 2. That's the domain restriction on the sine function in order to make it 1-to-1. All right. Questions? I think I'm at the end of my notes. So I want to show you the homework. So when I send this out, I'm going to send this file to you later today. Well, actually, yeah, you know what I might do? Just check your email. I might send you a link to a folder that I'm going to start putting our notes every day into. I think I'm going to do that instead. So this is the first 2 pages of this are your homework assignment. All right. So the first page, these problems here, on all of these, they give you a 1-to-1 function and they ask you to graph its inverse. I think you should do all of these. The first few have the actual points. So all you have to do is kind of flip the points over and plot them and draw your picture. But 31 and 32, these are more of kind of do your best. If you can identify some points, great, but try and just draw a pretty good reflection of that over here. Same with this one. So those shouldn't take too long to do those. Then 35, these right here, I tell you to try all of these, or I don't tell you, I just say for all of these, show that g of x is the inverse of f. In other words, show those two compositions spit out x in both directions. So you got to do f of g of x, you got g of f of x, and do that for all of these. These are all very similar to what we did. The hardest one is number 41. 41 is hard. 41 is like what I like to give on tests. All right, because there's a lot of subtle algebra in here you have to be careful with. All right, so I'm going to highlight that. Do not skip this one. Make sure you do that one. All right. And then after that, the next page, I'm only asking you to do the odds for this. There are functions that are given and you're supposed to find the inverses. So that's where you say, oh, let f of x be y, switch the x and y, solve for y. And some of these have domain restrictions. You see, this one has a domain restriction. So the ones that are circled are the ones that I ask you to do there. And that's it. That's it. Any questions? All right. I still have 20 minutes, so I'm not going to, I know y'all want to go. I know y'all are begging, like itching to go, but I think it's a good opportunity to kind of talk a little bit about the next section, just to get us, because there are things in the next section that always get me bogged down. I want to kind of just get the bogged down part out of the way right now. All right. So we're going to be studying these things called exponential functions next. All right. That'll be our next topic, exponential functions. And the way that I like to introduce exponential functions is with some demonstrations. So does anybody have a sacrificial piece of paper? You won't get it back? Thank you, Amanda. Okay. We have studied in this class how many different types of functions? So far, we have done linear functions. Linear functions look like y equals mx plus b, right? We've done quadratic functions. That equals y equals ax squared plus bx plus c. And then we did polynomials. And those, well, they look crazy, right? There's all different things they can look like. And same with rational functions. Y equals, well, we know it's a fraction, like a polynomial over a polynomial. And for each one of these different types of functions, they're all good for certain things in the real world. Linear functions are good when, like, maybe you make so much money per hour and you're trying to, graph like how much income you have. Quadratics, I told you all about, like satellite dishes and launching bombs and things like that. Quadratics are good for that. Polynomials are good for anything that oscillates stock market, income for a company, whatever it is. That's what it's good for. Rational functions, really good whenever you have things that kind of head towards zero, right? I started that whole conversation with that quote from the movie, right? Or if you have these vertical, like asymptotes where the function takes off, right? Never goes, but never passes something up. So all, functions are used because in the real world, what we're trying to do is take the real world, find something mathematically that models it, and then, study these, learn how to graph them, learn their behaviors, their properties. So what I'm going to do now is try and motivate a new function by giving you an example of something. And I think you'll see when I do this that none of these work for what I'm about to show you. All right. So in front of you, I have this page, right? This paper. And what I'm going to do with this paper is I'm going to start folding it. Okay. So I'm going to start here with the table. We're going to do good old fashioned T table. All right. Here I'm going to put in the X, where the X is, I want the X to be the number of folds I make in the paper. And the Y, I would like for that to be the number of rectangles that you see. All right. So right now, how many rectangles do you see? One, right? How many folds have I made? None, no folds. So when I have no folds, I have one rectangle. Looking at that like an ordered pair, that means the input is 0, the output's 1. As a function, I'm taking 0, it's spitting out 1, right? Do we have any function that could do that? I'm sure we have plenty of functions that could do that. I could think of a linear function right now that would do that. F of y equals x plus 1. If you plug in 0, it spits out 1, right? Okay. So nothing too special yet. Now I'm going to fold it one time. And when I open it up along that fold, I'm going to draw a line. Okay. So I folded it once, and you see how many rectangles now? 2. Okay, so now 1 gets sent over to 2. I don't know, is there a function that I could figure out to do that? A line? Can I get a line to do that? 2x, x plus 1? Does x plus 1 work? Does 2x work? So if I do 2x, what's wrong with 2x? When I plug in 0, I don't get 1, right? When I plug in 0, I get 0. It does work for this, though. It works for that one. For 1, if you plug 1 into this, you actually get 2. So this works for the second one, but it doesn't work for the first one. I'm trying to look for something that works for both. And the x plus 1, I think, still works, doesn't it? Yeah. Plug in 0, you get 1. Plug in 1, you get 2. So far, this looks linear. Second fold. I'm going to open it up. How many are you going to see? 4? Seem reasonable? All right. Do I have to draw lines each time, or can y'all see the folds? Y'all can see it, right? 4. 2 folds, 4 rectangles. One more time. How many? 8, 6. 6 and 8 are the most common answers I get. 6 and 8. 7, 1.65. How many do you see here? 8, 3 folds, 8. Now, if we start investigating this, no line is going to work anymore. All right, no line is going to work. If I go to Desmos, I can ask Desmos to start graphing these points for me. Okay, the first one was 0, 1, right? The next one was 1, 2. So those two live on a line, right? Those two live on a line. So I could find the line through that. But the next one was 2, 4. Okay, can you see that those no longer lie on a line? Doesn't look like there's a line through all 3 of those. And if I do the next one, 3, 8, it's off the screen, but there it is. It's curving, right? Maybe a parabola. Maybe there's a parabola that does this, or some polynomial, or maybe some rational function. Maybe. I don't know. Let's go again. 4th fold. What am I going to see? 16, 12. What's happening here? It's hard to see it, but I've got 4 across the top, and I've got 4 squares down the side. This is 16 now. So what's the pattern that you're seeing here? What's happening each time I take a fold? From here to here, though. Here to here. Here to here. Here to here. What's the next one going to be? You're multiplying by 2 each time, right? You're doubling. So when I do 5 folds, I should expect to see 32. It's getting hard for you to see the creases, but I'll count them out. We've got 1, 2, 3, 4, 5, 6, 7, 8 across the top, and 1, 2, 3, 4 down the side. 8 times 4 is 32. I think we have the pattern, don't we? I think it would be safe to assume that if we do 6 folds, we should get 64. So the trouble here is not that we can't find the pattern. The pattern's great. Here's my question though. If I asked you how many we would have with 15 folds, can you tell me quickly and easily? Or are you going to have to first figure out, go from 6 to 7, then 7 to 8, then 8 to 9, then 9 to 10, you know, and work your way down the table till you get to 15? Or is there some function that will take the input X and spit out the correct output for us, right? Do you have a question, or you think you know what it is? Can you hold on? You probably see it, but I just want everyone to understand what we're trying to do. Create a function that doesn't require we fill out the rest of the damn table to get to 15. We want to just be able to plug 15, you know, and do it. So now, do you see something? What do you see? 2 to the power of X. Interesting. Is that it? Well, let's go back and look at all these numbers. They all have something in common. Let's see this. I'll start with 2. 2 is 2 to the first power. And yes, 4 is that times 2. So that would be 2 squared. The next one is 2 cubed. The next one is 2 to the 4th. The next one is 2, another 2 added, right? Or not added, multiplied. And then keep on going, right? And all of these exponents, right, that you see, 6, 5, 4, 3, 2, 1. Those are just the X's, right? That's the number of folds. Which would mean that if I wanted to know this, maybe it's 2 to the 15th power, right? Which means that the function is something like this. We have never seen this before. Well, we're acting like, if you have, you're going to act like you haven't. Have we ever seen a function in all of the functions we've looked at in this class, linear, quadratic, polynomial, rational? Have we ever seen the X somewhere other than on the bottom? It's never been up as one of the exponents, right? We've had X cubed and we have X to the 4th and 5th and 6th and 7th. We've had all sorts of crap going on here. We've never seen X be up top like that. This is the first time we have something that X actually appears up in the what? What is that called up there? The exponent, right? That's called the exponent, and the number on the bottom is called the base. So this is the first time we've seen X up in the exponent. This is a special category of functions. What should we call them? Exponential functions. Why? Because X is up in the exponent. Okay, let's call them exponential functions. By the way, can someone do 2 to the 15th on their calculator? You should have a key on your calculator, depending on your calculator. A lot of calculators have this thing called a caret key, and that's how you raise things to powers, 2 to the 15th. 32,768. Woo, that got big fast, didn't it? This thing is getting big really fast. 2 raised to the X. Let's go to the computer and graph it. Y equals, you don't want this back, right? Y equals 2 raised to the X. There it is. There's the graph. Look at what's going on here. That sucker is taken off, right? Look at that. It went up there. I mean, we plugged in 15, which 15 is like right here. 15 is like right there, and it's already way up at 32,000. This is growing rapidly, isn't it? Very rapidly. Is it growing faster than X squared? Let's see. If I graph X squared, there's X squared, right? There's X squared, the good old parabola. So look right here. Do you see that the green function is above X squared here? What happens? What happens? If I keep going, where do they? There is a point right here. This is where the green one takes over. Do you see that the green one is above the purple one here? And that means that the green one's growing faster. And if I keep on going up, look at how they start to spread apart. So if you were to pick an X value, just take this little line right here, follow it you know, down, it would hit the purple one way down there, and it's going to hit the green one up here. So the green one is above the purple one. So it's growing very, very quickly. How am I doing on time? Okay. All right. Yeah. No. So this is our first kind of look at exponential functions. Do you think that all exponential functions have to look like 2 raised to the x? Or do you think we could use a different number down here? Yeah, why don't we use 3 to the x or something like that? Now, that would not be this situation. This situation right here, folding, is 2 to the x. But we can have other things in the real world where it's maybe 3 to the x. An example of that would be bacteria growth. Let's say you start with bacteria. Okay, there's one bacteria. You put it in a petri dish, right? And let's say this particular bacteria, every hour, it splits and becomes 3 bacteria. So boom, boom, boom. After 1 hour, that's what happens. Okay, what's going to happen an hour later? Now you're going to have 9. Right? That's after another hour. So this is 2 hours after the whole thing started. Then an hour later, each one of those goes again to 3. So what's happening is this: at time equals, this is number of bacteria, at time equals 0, you had 1 bacteria. 1 hour later, you had 3. 2 hours later, you had 9. 3 hours later, each of those 9 triple, go into 3. So now you have 27. These are all powers of 3. 3 to the first power, 3 squared, 3 cubed. You know, see that? So this looks like 3 to the x. And if we graph that, let me get rid of the x squared. If we graph 3 to the x, that actually is growing even faster than the 2 to the x. It's even bigger. And if I did 4 to the x, it'd be even bigger. 5 to the x, bigger. 6 to the x, right? Okay, so we're going to be studying these, all right? We're going to get a good feeling of what they are, what they do, how they behave. And then after we study them, we're going to talk about, do they have inverses? So just by looking, do these have inverses? Do these look 1 to 1? So they should have an inverse. And that's what a logarithm is. We'll learn about logarithms are the inverses of the exponential functions. Okay, I'm almost done. I just want to say one more thing, and this is kind of like off topic, on topic. Does anybody recognize these numbers? I want to continue this table a little bit. What would 7, if I did 7 here, the next one would have been 128, right? They're just doubling each time. And the one after that, if I plugged in 8, would be 256. 9 would be 512, right? Do y'all recognize these numbers at all? Do you ever see these numbers in the real world? They are multiples of 2, yes, but do you ever see them in the real world somewhere? Do you have a phone? What kind of phone do you have? Really? Is it kind of new or no? Do you remember how much memory, how much storage space it has? How much storage does it have? Oh, you don't need to look it up. But do you recognize those numbers as your choices? Right? 256 gig? Or are you going to go with the 128 gig, right? You recognize them? So why is it that computers use these numbers? This is kind of pointless at this point. Why did they use these numbers? Yes. That's exactly right. A computer only understands 2 things. Okay, so these complicated machines that we have, right? I'm streaming my video, right? All this, my audio is coming through, everything's being projected, right? Through all these cables and wires and stuff. All computers can do is have basically a switch that's either on or off. It's like a light switch, yes or no. There's an electrical signal or there's not. That's all a computer knows. And so we can basically break that down into 2 possibilities, either a 0 or a 1. That's it. There are only two states that it can be in at any particular moment. It's constantly checking yes or no, yes or no, yes or no. That's it. That's all a computer knows. So that's called binary, two choices. And if there are only two choices, that means that everything in that system is going to be 2 to some power because there's only two choices. And that means all, memory, storage, all that stuff should be in these powers of 2 clumps. And that's why all, phones storage is 256, 128, all that, right? That's called binary. Now, our number system that we work in is called base 10. This is base 2. Our number system that we use is base 10. And our number system that humans use, right? The only possible digits that we're allowed to use are these, right? Every number that you ever use in your life can be formed using those numbers and decimal points, right? That's it. That's our whole number system. That's called the base 10 number system. We could, if we wanted to, use binary. Binary is just perfectly suited to do all the math we do. We could do it with just zeros and ones. We do it with this. Does anyone know why we use base 10? Base 2. Does anyone know why we use base 10 and not base 2 or base 8 or base 16? Anyone know? I mean, there's a really important reason why. It is unique to us. Go ahead. We have 10 fingers. We have 10 fingers. Okay. So when we started counting, right, this is what made sense, right? We assigned something to each one of these, right? So it was, 1, 2, 3, 4, 5, 6, 7, 8, right? But then we have 0 in there also, right? So because of 10 fingers, our system is base 10. If we had 8 fingers, I'm willing to bet my life we would be using base 8, if that's what we humans had, 8 fingers, right? And for us, it's like base 10 is just, we don't even think about it because that's what we're born into and we don't even question it. But that's the only reason we use it. That's the only reason, okay? All right, we got to go. 2:41, sorry to keep you. Y'all have a great weekend. Make sure you do this homework. I'm going to send you all that link. I'm going to do it right now so I don't forget.
Have a good one, sir. See you
You
Monday.
too.